this. Is it working now? Okay. So yeah, thanks the organizer for the invitation to this beautiful place. So it's my first time in Cabo Frio. So I enjoy it. I enjoy the view and the wind very much. Okay, so my aim is to discuss. Okay. B-divisors. Yeah, maybe. And application, so probably I'm going to talk about application to dynamics in the last talk. But the plan is to talk about application to the volume function, so linear series, and maybe to dynamics, to algebraic dynamics. So the aim is to define what B-divisor is. So B stands for birational. And essentially to tell you what a NEF B-divisor might be, and to develop an intersection theory of such objects. Ay, ay, ay. So interestingly enough, this is very much algebraic in nature, but the ideas that lies behind, or in fact comes from complex analysis. So there is some kind of mixture between algebraic geometry and some idea from analysis also. So I hope that you will like it. So, okay, so today my aim is to do some yoga. So I'm far from being flexible. So let's say yoga of B-divisor. So let's say B-yoga. So define what a B-divisor is and what is the difference between Wahl and Cartier B-divisor and so on, intersect them. Then tomorrow I plan to talk about the volume of line bundles and to see how to use B-divisors to prove that the volume function is actually differentiable. Then the third talk, so I'm not going to tell you what I'm doing in the fourth talk because it's like too far from now. But I plan to talk about intersecting theory of NEF B-divisors and maybe algebraic dynamics. Okay, so I see that my main problem is going to be chalk, right? Okay, so let's start with the divisors. So I'm going to start very slow, and then after the defining divisors, I'm going to B-divisors. It's just to make the setup completely clear. So X will be a smooth, projective variety. So reduced, irreducible. Over your favorite field. So mine is the field of complex numbers. So I guess that I'm going to assume that the field is characteristic 0 and algebraically closed. And D stands for the dimension. Okay, so you already know, but so let me redefine what a Wahl divisor is. So this is a formal combination, let's say Z. Okay, I should have prepared slides. So it's a finite formal combination, some AI ZI, where AI are integers, and ZI are prime divisors inside X. So codimension 1 irreducible subvariety. So the set of all Y divisors, I'm going to denote it by W of X. And so this is a free abelian group. It's huge. And sometimes I'm going to look at the Q vector space or R vector space generated by this. So it's W tensor Q over Z and same so for WR. Okay, so if you have a Wahl divisor and you have an open subset, let's say affine U inside X, you can always restrict it to U. And yeah, okay, well, I'll start with smooth, but in fact I wanted to say normal. Sorry. So later on it's going to be smooth. So since X is normal, if you have two divisors that agree on some open subsets, then they're equal. And so if you have a meromorphic function, let's say phi defined over X, then you can look at what I'm going to denote by d of phi, which is the divisor of its zeros and poles. So okay. So now you have a subset of the set of all divisors, of Wahl divisors, consists of Cartier divisors. So it's there are Wahl divisors locally defined by an equation. So let me denote this set as C of X. C stands for Cartier. So this is a Wahl divisor such that for any such that you can find a covering of X by open chart. So that the restriction of Z to UI is defined is the divisor of pole and zero of some meromorphic function on UI. Okay? So first observation is that, so in general, so by definition, so C of X stands inside, it's included inside W of X. So subspace if you want of W of X. But you may have a strict inequality. So you have equality, sorry.
Do you mean that this restriction to U, that the complement has a dimension at least 2?
There is a covering of UI such that you have this.
I mean on the restriction. And you have like divisors on the complement of U, maybe?
What am I saying? I think I said something completely wrong. You're right. Anyway, yeah, it's not very important. Yeah. Yeah, you're right. If the codimension, let's say, okay, if the codimension of U is at least 2, then you have this. Yeah, I don't know why I wrote this. Okay, sorry. Okay, so you have equality if X is smooth. Or even if, so you have equality here between the Q vector space if X has mild singularities. So I'm not very precise about what mild means. For instance, if X has only quotient singularities, then you have equality like this. But in general, you have strict inequality. Okay, so you can naturally, when you have a map, F, so you have natural transformations. So if you have a morphism, let me assume here that X prime X have the same dimension. And then F is dominant. To avoid problems. Then you have natural morphism, so you can push forward Wahl divisors. And you can pull back Cartier divisors. So I think that Cinzia already defined the push forward, so let me do it again. So suppose that Z is an irreducible, it's a prime divisor. And so you want to define the push forward of its class. So if the codimension of f of z is at least 2, so somehow if z is contracted by f, then you set the push forward to be equal to 0. And if otherwise, f of z is a prime divisor, and then you set the push forward as being the class of f of z multiplied by some integer. And the integer is the degree of the restriction of a map from z to f of z, which is also the degree of extension of c of z over c of f of z. Okay, so here degree, I don't know exactly what you mean by this, but it's topological degree. So if you want c of z over c of f of z. So this defines a linear map, so on WQ to WQ. And now you can define the pullback of Cartier divisors. So let's say U, or maybe U prime is an affine chart, which is mapped by F into U, which is an affine chart. And Z restricted to U is a divisor of pole and zero of some rational map phi on U. Then you define the restriction of the pullback of Z on U prime by pulling back this phi. So D of phi composed with F. Okay? So let me just add one comment here, is that in general, if you have bad singularities on X or X prime, it's impossible to, so you cannot define the pullback of Weil divisors naturally, but on surfaces, there is a canonical way, let's say, to extend this pullback on Cartier divisor to Weil divisors, to pull back Weil divisors. So it's based on the intersection form. So it's called the Mumford pullback. I'm not going to use this. It's just to mention it. So I'm going to work mainly in dimension 3 and higher. And so in general, I cannot pull back any Weil divisor, naturally. Okay, so now B-divisors. So what is a B-divisor? A B-divisor, it's a divisor not defined, which is not defined necessarily on X, but it's defined in some birational model over X. So to define this properly, I need to tell you what a birational model over X means, okay? So the heuristic is a B-divisor is a divisor, so either Weil or Cartier on some birational model over X. So what is the birational model over X? I will really have problems with chalk, I think. Okay. Okay, so it's a map. It's a morphism, let's say pi from x pi to x, which is birational. And I assume x pi to be also projective. And normal, et cetera, et cetera. So I'd like to consider, so here I have to be careful. So let me say it's the set of all birational models. It's not, so there is a small category issue here. It's not really a set. It's more like a category. So if you look at the space of all birational model up to isomorphism, then it's naturally a set, because if you have a projective birational morphism like this, then it's necessarily isomorphic to the blow-up of some covariant sheaf. Covariant ideal sheaf on X. So the set, so you can talk about the set of all covariant ideal sheaf on X. And so up to isomorphism, you can realize M of X as a set. So I'm not going to, I'm always going to say the set of all birational models, even though I should be a bit more careful here. I don't think this makes any difference. Okay, so this set is endowed with a partial order. So you have a domination, let's say partial ordering. So if you have two elements, pi prime and pi inside of M of X, so two birational model over X, then you say that pi prime dominates pi if you have the following diagram. So pi prime and pi are birational. So you can look at mu, which is the map pi prime composed with pi minus 1. It's also birational. And you say that pi prime dominates pi if and only if mu is a morphism. Okay? So it's a fact that M of X is a so-called directed poset. So what does it mean? It means that if you take two birational models, so maybe they are not comparable one to the other, but you can always find a third one that dominates both of them. Okay? So let me write it maybe here. So it says that if pi prime and pi are two birational models, then there exists pi double prime, another birational model, such that, so here are the canonical maps. So such that pi prime dominates pi, pi double prime dominates pi prime and also dominates pi, okay? So how do you do that? Well, you look at this map, mu. So if mu is a morphism, then you set pi double prime equal to pi prime, but in general, it's just a rational map. And so you can look at the graph. So x double prime you can take as the graph of pi double prime. Irreducible subvariety inside the product. And the projection onto the first and the second components are exactly given our morphism. So, no. So when I take the graph, I'm taking the graph over the set of points where it's defined, taking the closure. So here I said that I want to normal models. So probably I have to take a normalization of this. Okay? Yeah.
So given any pi and pi dot, is there
If you have pi prime and pi, like this, so a priori, they are not comparable. Okay, let me give like a very simple example. So let's take x equal to p2. And then you take 2 points, p and p prime, distinct points inside p2. So you can let's say, pi to be the blow-up at p, and pi prime to be the blow-up at p prime. They are not comparable. But then if you can choose pi double prime as being the blow-up at p and p prime, okay, it's going to dominate both of them. Is it clear? Okay, so comment, observation. So the theory works in a very general context, normal variety and so on. But I'm going to, here, since I can replace any birational model by another birational model that dominates it, and I'm working in characteristic 0, I can use a resolution of singularity. And so in what follows, I'm going to replace this category here, M of x of all normal birational model, by a smooth birational model. So I shall replace M of x by the category of all smooth getting smaller and smaller. Okay, so let's define now Wahl B-divisors. Okay, so Wahl B-divisor is, let's say, a function. I should not say this because I said that M of x is not a set, but okay. It's a function that to any pi inside M of x, so any birational model gives you some Wahl divisor inside x pi. Okay, so Wahl divisor is a collection. It's a collection of Wahl divisors in all birational model over x, but with some restriction, with some compatibility condition, if you want. And the compatibility condition is that if you have pi prime that dominates pi, so that this canonical map from x prime to x pi is mu is a morphism, then you want mu, the push forward of z p prime, to be equal to z. Okay? So I'm going to denote this space of all B divisor by W of script x. And you can define adequate also WQ, WR, etc. Okay, so there is another way to think about Wahl B divisors in terms of valuations. So let me describe it. So alternative way. So let me recall what a divisorial valuation is, at least for me. So this is a function, let's say V, from the set of, from, let's say, the field of all rational function on X that are non-zero to R, in fact, to Z, such that, so V of F is the generic order of vanishing along some prime divisor. So E is a prime divisor, maybe in X, but maybe in some model over X. So in some x pi for pi inside M of x. Well. Okay, so what is a Wahl B-divisor? In fact, this is the same as a function, let's say g of z, on the set of all divisor evaluations. On X with one finiteness condition, okay? So let's say on X, on any model, you want only this function g of z to be non-zero on finitely many prime divisors. So this finiteness condition is like this. So for any pi inside M of X, so the set, let's say, of prime divisor E inside x pi such that gz of ord E is non-zero is finite. Okay, so I mean, I don't know, if you prefer geometry and divisor, you think this way. If you prefer valuation spaces, you can think of a divisor like this. So in fact, it's quite interesting to think in terms of valuation, especially, so this point of view is especially interesting in complex analysis. And algebraic dynamics. For the following reason, is that for some special B-divisor, sometimes the function here can be extended in a unique way to a huge set of evaluation, not only divisor evaluation, but any evaluation, okay? So it's a very standard procedure in algebraic dynamics. Okay, so what are the main examples of B-divisors? So I've been talking for half an hour, right? So the main examples of B-divisor, I'm going to call them Cartier B-divisors. So let me explain what this is. A Cartier B-divisor is something like lives in some finite model. So it's a divisor. It's a Wahl B-divisor living in some fixed birational model. Let me explain what this means. It's just a heuristic here. Okay. Okay, so we say that Wahl B-divisor is Cartier if the following holds. So if there exists some model, let's say pi naught, and a class, well, such that the following holds. So you have x pi naught here in the middle, x here, x pi would be here. So what we know is that for any model, there exists a model, let's say x pi prime, that dominates both of them. So let me call this map alpha and this map beta. So here you have pi naught and here I have pi. So the condition is that z pi is obtained as follows. Is obtained by pulling back by alpha z pi naught and then pushing forward by beta. Okay? So when I say Cartier B-divisor is living in some fixed birational model, then here what I would mean is that essentially, so this Wahl divisor is determined by its incarnation, so z pi naught inside this model. Because after, when you get up in this tower of all birational model, what you are going to take is only pullbacks. Okay? So then, of course, if you want to have this condition, you need to force this equation. So when this is satisfied, I will say that Z is determined in X pi naught by Z pi naught. Okay, and I'm going to fall. So many technical problems. Yeah, sure, sorry. I will be the first? Oh, okay. Yeah. From now on, all models are smooth. Yeah. So Cartier and Wahl divisor are the same. Okay. I don't want to care too much about this. Okay.
So, are you going to give an example where this property does not hold?
Yeah. You'll see. There's a very famous one, So there is a canonical B-divisor, and it's at least from dimension 2 on, it's never Cartier. Okay. So. Okay, so let's define C of script X. So this is a set of the space of all Cartier B-divisors. And so this is a subspace of this, by definition, of W of script X. So we have this observation also, is that if you fix any birational model, then you have a canonical map from the space of Cartier divisor inside X pi to C script X, which is defined as follows. So if you take W in here, then you force this equation. So then you attach W pi, should say pi naught here, W pi, such that this equation here is satisfied. And it's not difficult to check that this is an injection. And so one way to think about this is somehow that the space of Cartier B-divisors, in a sense, is the union of all the Cartier divisors in all birational model over X. So I'm just going to write down something like a formal. It's not really essential. But so M of X is a directed poset, so you can talk about injective inverse limit and direct limit. And C of X formally is a direct limit of all this a space of Cartier divisors, and W of X is the inverse limit of the same thing. So here I'm not very careful because, as you said, I'm assuming that M of X, that M of X contains only smooth models. Okay, so maybe two things. So maybe I'm going to write down two things. So let me explain a little bit more what this means here. So let me take two divisor. So W, let's say in X pi, and W prime in X pi prime. So maybe I should give a notation here for this map. So if I have a divisor in some model, I'm going to denote by C of W, C for Cartier. I could have done small b of this, but so C of W is going to be this Cartier B divisor over X, okay? So what is the condition? So now what I'm taking two different models and two different divisors on these two different models. I'd like to understand when these two different divisors define the same class inside W of X. So these two B-divisors are equal. So if and only if, so there exists pi double prime that dominates pi and pi prime. So just as, well, like this. And the condition is that the pullback of W by alpha is equal to the pullback of W prime by beta. Okay, so now I'd like to give one very important example of B-divisor that is not Cartier. It's the canonical B-divisor. So to avoid difficulties, I'm going to assume the X to be smooth. And I'm going to take omega, top meromorphic, I should say, a top form, top differential form. Okay. Rational, I'm sorry, I was looking, it's a rational top form. And let me look at K of X. So K of X is divisor of pole and zeros of this top rational top form. Now if I take any birational model, so remember that x pi is supposed to be smooth. And what I can look at k pi, which is going to be, well, the divisor of pole and zero of the pullback of omega. Okay, so it's a canonical divisor also for k pi. And I'll let you check that the push forward of k pi here is equal to kx, or more generally, if pi prime dominates pi, then the push forward by mu of k pi prime is equal to kx, to k pi. And so this collection of divisors of k pi form a B-divisor, usually denoted by k script x. And it is not Cartier. So why is it so? So you take any x pi, and you look at x pi prime, which is, so take any point here inside x pi, and look at the blow up at the point P. Okay? So now if you look, so this is what I call mu. If you look at the pullback of k pi, if I'm not mistaken, it's k pi prime. Yeah, I have to be careful in this or sign. So let me this way. So k pi prime is the pullback of k pi minus the exceptional divisor, and so it's never zero. Okay, so each time you're going up in the tower, then this canonical divisor is changing. So it's not defined at some fixed level, okay? So it's not Cartier. Well, okay, except in dimension 1, but I'm going to assume that the dimension is at least 2 everywhere. Sorry? Yeah, up to sign. Yeah.
You mentioned the finiteness condition.
Yeah.
But now I see I did not understand it. Can you repeat?
It's just that, so look at, okay, P2. If you take, so you have a lot of divisor evaluation. So for any curve, maybe singular, whatever, irreducible, you get one divisor evaluation. But what is a divisor? A divisor is a finite linear combination of curve inside P2. So you need a finiteness condition. No. Okay, it's a finiteness condition at each level. At each level, for any model, you want the space of a prime divisor living inside this model to be, I mean, the one that contributes to the divisor to be finite at each level, okay? But yes, as you see here, you have contribution that appear for, I mean, at all infinitely nearby points if you want, and you have infinitely many points like this. Okay. So, yeah, so I'm not going to make the history, so I'd like to make some historical comment. So I'm going to put some names on the blackboard and to give some hints of where B-divisor could be useful. So I think that the first time this notion appeared was in the work of the Russian school, so especially by Yuri Manin on cubic forms. So it's very much related to what Susanna is describing. So he was interested in birational transformation of smooth cubic surfaces over non-algebraically coarse fields. So this is very, very clearly related to what Susanna is discussing. And then there is a very important, so I think this this terminology of B-divisor was introduced by Shokurov on his very famous paper pre-limiting flips. And so, okay, I'm not a specialist in minimum model programs, so I don't know how profound this notion of, or how important this notion of B-divisor is in this program. But I found, let's say, a recent paper that with 11 authors, including Kovac, that were playing with, well, proving the MMP for B-log canonical divisors. So it's still something that it's under, let's say, work. So B-divisor for an MMP. So here it's around, I don't remember, maybe late 70s, early 80s, and here in 90 something. So then around 2005 and so it was realized that it's, they play a role in the study of asymptotic linear series, especially when you want to define the Zariski decomposition. Of big divisors. So this was realized by Buxom, Johnson, and myself. And there is some work also of Couronia and MacLean. And so this is what I'm going to describe tomorrow, probably. So, and then, so maybe it's 10. So Buxom Johnson realized also that you can be applied to study singularities of many sorts. And not only algebraic singularities, so singularities of objects that are like close to being algebraic, but not exactly. So PSH functions and positive closed currents. And also it intervenes in many problems in algebraic dynamics. Also in the study of the Cremona group. So this was realized by Serge Cantat and many others, so Johnson, myself, and so on. And so the last maybe piece of work that I'd like to mention is so B-divisors of this idea to look at divisor not only in one model but all birational model over it. It's very useful when you try to understand the discrepancy function that appears while defining classes of singularities in the model, minimal model program. And so there are a lot of work, in particular by Duffernex, Buxom again, myself, and also more recently by Chile, Shenyang Xu, etc., on, let's say, how to use this B-divisor to study singularities that appears in the MMP. So all this is vague, but if you're interested, I can give you some more references. Yeah, okay. So also there is a notion of case stability that Buxom and Johnson have been working on a lot, and they use B-divisors all the time. Okay, so in fact, I'm not going to talk too much about B-divisors, but it will be more important to talk about B classes. Okay, so what I'm going to do is somehow to redo this kind of definitions, but now for divisors now, but for classes. So either of curves or numerical classes, either curves or divisors, I mean any codimension. Okay, so I will spend the rest of of my talk talking about this. So B classes, so I should say B numerical. Sorry? B birational. Why not? Yeah, so for instance, so in the in application to understand the hierarchy decomposition or even algebraic dynamics, it's really essential not to work with with divisors itself, but with classes. Okay, so space of numerical classes is a very small space, and so this is really essential when you try to understand some basic properties of dynamical system, for instance. Okay, so yeah, so from now on, X is smooth, dimension D, and probably at least 2, and probably at least 3. So Nk is any number, any integer between 0 and D. And so I'm going to look at Nk of X, which is the space of codimension K. So here I'm going to insist, so smooth is going to be essential because I want to do intersection theory, okay? So codimension K cycles modulo numerical equivalence. So we saw here in Cinzia's lecture the case where K is equal to, so here it's an N. So K is equal to 1 or K is equal to D minus 1, but probably I'd like to discuss all cases, okay? So Z now is the sum of AI, Zi. So as before, so this is an integer. AI is an integer, and Zi is a codimension K, irreducible subvariety inside X. And so you say that 2 cycles like this are equivalent if all their intersection with respect to dimension K cycles are the same. So Z, the numerically equivalent to Z prime if the intersection with C is the same for any cycle. So dimension K cycle. Okay, so here it's absolutely unclear what this means. So I'm going to assume that you have read this wonderful book by Fulton. I didn't. Okay, so at least when K, I understand what's happening when K is equal to 1. So here Z is Cartier automatically, so it's attached, so you can look at, you have the line bundle which is attached to it, or x of z. Let me call it L. And so what is this thing? Well, you can restrict L to C. So C is a dimension 1 cycle. Let me assume that C is irreducible, so it's just a curve. So you restrict L to C, so you have a line bundle on a curve, and you can take its degree. So this is some number, okay? Okay, so if you're knowledgeable enough, then you know how to define this intersection theory using deformation to the normal cone. But otherwise, I assume that my field is over C, and so you can use Durham cohomology. To understand what is this number. Okay, so let me assume that Z, let's say, is irreducible of codimension K, and same, C is irreducible of dimension K. So if, So if Z is in a codimension K, irreducible subvariety inside X, you can look at its fundamental class. So even this is not completely clear what this means, so at least what Z is smooth, this is something which lives in the homology. By Poincaré duality, it lives in the cohomology, let's say, over R. In fact, it's with the integral coefficients. So this is a fundamental class. So I'm a complex analyst, so one way I think about this is that Z defines a positive closed current, KK current. So it's not exactly a differential form, but it's a linear form on differential forms. And you can define the Durham cohomology of current, which is isomorphic to the direct cohomology on differential forms. And since this guy is closed, it defines a class in here, okay? Or you do the standard thing in to attach, to define the fundamental class. Anyway, so you can do the same for C. Now it's in H2D minus 2K XR. And so what is this intersection number? Well, this is a pairing. So you have two classes. So here, let's say it's Durham, okay? DR is for Durham. And so you have a pairing from H2K to the complementary dimension, H2D minus 2K. And so this is a number. So it's a priori, it's a number which is real. And then you can, in fact, use Fulton theory to check that it's integral. So here it's pairing in Durham cohomology. Yeah, I'm really sorry for my handwriting is already quite bad. I'm doing my best. Okay. So a very important thing is that, so yeah, one can prove, in fact, this belongs to Z, right? So very important thing, theorem, is that nk of X is a finitely generated abelian group. So in fact, I'm going to use, I'm not going to use nk of X. I'm always going to use the vector space, either defined over Q or over R. And so what I'd like to just to recall is why these vector spaces are finite dimensional, which is weaker than this statement. In fact, the proof is the same. So let me indicate how this works. So you look at V, which is a vector space, let's say, defined over Q. So I want to show that nk of X over Q is finite dimensional. So you look inside the space, inside the Durham cohomology, of the right degree, so probably 2D minus 2K, the vector space generated by classes of dimension K reducible subvariety. Okay, so we know X is projective, is compact, so we know this guy is fine dimensional. Okay, so maybe I'm going to look at this, right? So this guy is finite dimensional, hopefully, and so this one also. And so I can find finitely many dimension K subvarieties, C1, Cn, such that their classes generates V. Okay, and now, so I hope I'm not mistaken. So you look at the space of all cycles of codimension K, and you look at this map to R to the power n. So n is the number of cycles I've chosen here. So to Z, I'm attaching this intersection, so Z against C1, Z against Cn. Okay? So the observation is that, so this guy is infinite dimensional. But the observation is that if you look at cycles that are numerically trivial, then they are mapped to 0 under this map. Okay, so they lie in the kernel. So it means that you have this map factors through the space of numerical cycles of codimension K. And because they generate all this vector space, in fact, you can check that this is an injection. Okay, so this is fine dimensional, dimension n, and so this has to be fine dimensional also. Okay. So, okay, if you're not over C, you need to argue exactly the same way with étale cohomology and so on and so forth, but so yeah, I prefer this kind of thing. So that's why I use also. So it's true over any field, not only over a field characteristic 0. Okay. What do I want to do? Yeah, so probably I would like to define Wahl numerical classes, Cartier numerical classes, and so on. So what do I need? Yeah, I need a couple of things. So if F is a morphism, and so then you have an induced mapping on numerical classes, so from nk of x prime to nk of x, which is defined as before. So this is equal to 0 if the codimension of f of z is strictly larger than k, and otherwise is e times f of z if the codimension is exactly equal to k. So you have to check that it goes down to the quotient. Okay, so once you have this, you can define as before the space of, so let's say Wahl B numerical K classes. Let's say, so this is W for Wahl, nk of script x. And what I would like to do is something like the inverse limit over any pi inside m of x of nk of x pi. Okay, sure. So what does it mean? It means that an element in here, let me call it alpha, this is a collection of classes, alpha pi. So alpha pi is in nk of x pi, such that the compatibility condition is satisfied under pull forward. So if, as before, so if pi prime dominates pi, and mu is the canonical morphism relating these two, then you want mu, the push forward by mu of alpha pi prime to be equal to alpha pi. Okay, so one thing is that pushing forward cycles is okay, but pulling back is more difficult. Yeah, so in codimension 1, it's, you can always pull back equations, that's fine, but in higher codimension, this is a cycle is not necessarily of complete intersection and so on, and so it's more complicated. So to define pullback, you need to use intersection theory again. So fact, let me call this Poincaré duality. Yeah, I know well. So yeah, you have realized I'm French, so you had de Rham cohomology and then Poincaré duality, etc. Yeah. Duality, if you want. So okay. So for any k inside 0, from 0 to d, so you have a canonical map. So this intersection theory between intersection, a pairing between product, they go down by definition to numerical spaces. And so you get, so let's say, let me focus only on R vector spaces. So you get a pairing from nk cross nd minus k to R. And this pairing is perfect. So what does it mean? It means, so this is the intersection pairing, right? So the intersection pairing. So it means that if you have alpha in nk, and if it turns out that alpha intersect all cycles of dimension k, or orthogonal to all cycle dimension k, so for all beta, then in fact alpha is equal to 0. Okay? Exercise. Okay, so but now you can, if you have this, and if you know how to push forward cycles, then you can pull back by duality. Okay, so you set f alpha, so exactly like this. So here maybe dominant. I don't want to, and equidimensional. So you define the pullback of a cycle, of a numerical cycle, by forcing this equality here. Okay, so now that you can define, so you have to check that this is, in codimension 1, you get back the pullback of a Cartier divisor, etc., and so on. It's compatible with this. And once you know how to pull back, well, you can define Cartier classes, which is, as before, the inductive limit of this. Okay, so I'm not going to write down again what this means. So this, so this thing here is a subset, a subspace. Let me write index R. So it's a subspace of Wahl B numerical K classes, okay, which are determined. It's numerical classes like this is Cartier if it's determined in some model as before. Okay, so in some model, if you go up in the tower of birational models, you have to take pullbacks. Okay, so sorry, how much time? It's over already? 25 minutes. Ooh, okay. I'm not sure I'm going to take 25 minutes. Okay, so yeah. So let's put all these spaces together and let's try to define some intersection numbers. So well, this is what I'm going to do. So I'm going to set Cn point. So this is a direct sum for k is equal to 0 to d of C and k. And the same for Wahl numerical classes. And so what I claim is that there exists a canonical pairing between B classes. Okay, so here I have to be a little bit careful. So there exists a canonical intersection pairing. So you cannot pair any Weil divisor with another one, but what you can do is you can pair, or class, so you can pair a Cartier class with a Weil class, okay? So you, and so Cartier class, or Cartier numerical class with a Weil numerical class, and the end result is a Weil numerical class. Okay. So what are the main properties? So it has to respect the grading. So it means that if I have a Cartier numerical class of codimension k, and I pair it with a Weil class of codimension L, then I should end up in the Weil class of codimension k plus L. Okay, sounds reasonable. And is continuous. Okay, so I didn't talk about topology, so probably it will be a good point to define this. So it's continuous in the second variable. And also, it's perfect. Okay, so you have to be a bit careful of what perfect means here. So perfect pairing, you probably want the end result to be a real number. So, and so if you look at the pairing from Cartier numerical K classes and Weil numerical D minus K classes, so you end up in R, and this pairing is perfect. Okay. So it's not very deep. Okay, well, okay, yeah, well, I should not say this. Intersection theory is very deep. So here it's just a matter of a routine check that Fulton intersection theory gives you something like this. Okay. So what I'm going to explain in the maybe tomorrow or on Thursday is that in some cases you can intersect some special Weil classes between each other, and this is difficult. But if you want to intersect Weil classes, you need some positivity for these Weil classes. So essentially, you need them to be Ampon or maybe Neff or something like this. Okay. So this is what I'm going to explain. So here, in fact, this is not very difficult. So what I'm going to do in this last 10 minutes. Yeah. So well, I can start. I mean, talking about the volume function, but probably you don't want that. So yeah, you wanted to ask something? No. So I'm going to define this this product here. Okay. And then I'm going to talk a little bit about the topology. So I didn't talk about topology yet. Okay. So how do you construction of the pairing? Okay. So how does it work? So you have Z. You take an element which is a numerical K, P numerical K classes. So Z is the Cartier class attached to some, let's say, cycle small z. Okay, so Z is a codimension K. cycle in, let's say, in x pi naught. And then you take a Weil numerical class of dimension k. So probably C. So this is an element of W. So let's say it's a cycle, dimension k. Well, I should not say this. So it's a family of dimension k cycles that are compatible under push forwards and whose classes define the element that you want here. Okay, and so you want to pair them. Okay, so I have to tell you what's this. Maybe this is maybe any. So it's probably dimension L. Okay, I don't need to. So here the pairing, you don't need to take a complementary dimension. So I have to tell you, so what will be the intersection of Z and C in some model pi, okay? So pi is some model. Okay, so here's the way you do this. So you don't have that many choices. In some sense, you need to force the invariance under push forward. So this guy Z is determined inside x pi naught. And so inside x pi naught, what you want to do is to intersect small z with c pi naught. Okay? Okay, fine. So you're going to do this in all other models. And what you want to check is that you want to check that you have compatibility under push forward. Okay, so how does it work? So we have x pi naught here. Maybe x pi is here. So you take x pi prime, which dominates the 2. So I'm trying to follow the notation of my notes. So here it's pi naught. So I have to tell you what is z intersected c inside pi. Okay, so what you do is that you intersect everyone here in x pi prime. So what is the class of this inside here? So this is a pullback of z by alpha, and you intersect with c pi prime. So this is a class in nk plus L in here, but then you want to push it forward down to x pi. So this guy is, so I have to take the class of this is in nk plus L of x pi. So what you want is you want to check that this does not depend on the choice of pi prime, and that this collection of classes satisfies the push forward compatibility condition. Satisfies the compatibility conditions under push forward. Okay, it's an exercise, but let's check that it doesn't depend on the choice of pi prime. So let me choose x pi double prime above x pi prime. So, okay. Let me call this map beta. And so what I want to check is that if instead of defining z, c inside x pi like this, so pulling back, inserting here, and pushing forward, I do the same thing, but in x pi prime, x double prime, I want to check that I get the same result. Okay, so so what's happening is that, so now you pulling back by alpha, pulling back by beta, the class z, and you intersect with c double prime. And the claim is that if you push it forward by beta, well, here you have I don't remember what's the name, but the product formula or something. So if you push forward a class intersecting with the pullback of some other class, in fact, this is push forward formula. So this is equal to beta lower star C double prime against alpha this. And since the collection of C pi is compatible over under push forward, this is exactly C pi prime. Okay? And so because of this definition here of this class does not depend on the choice of pi prime. Okay, well. Anyway, so what you see here is that here it is essential in this formula that one of the class is in fact determined by just pulling back starting from some birational model. So if the other class here were only veil, then it does not make sense. In fact, so you don't have like a invariance under push forward. And the same, exactly the same argument shows that they are compatible under push forward. Okay, so yeah, I guess I have some time, so let me discuss the topology. So the rest here of this of the statements are kind of follow from Poincare duality directly. So topology. So on what? Let's say on this vector space, okay? So I prefer to work on real vector spaces. So this guy is infinite dimensional. Okay, so it's not completely on infinite dimensional vector space. You have, in general, you have many different kind of topologies. But here the point is that this was defined as an inverse limit of nk x. And so by definition, this sits inside the product. Whoops. And as we saw, all these spaces here are finite dimensional, are vector spaces. So they all come with their canonical Euclidean topology, okay? So the point is that this so the point is that W here is a closed subset of this product. I'm not sure how to should write this like this, nk. And so you can put you have a natural topology on this space that comes from this embedding here. And so for this topology, Wnk is locally compact. Okay. I'm going to say a bit more. Okay, this is very abstract. Usually I don't like to do it this way. So the point is that here you're taking a product over, in general, uncountably many things. So you cannot characterize a topology in terms of sequences. But I'm going to pretend that this space is countable. And in this case, the topology is much, much nicer. So this happens, for instance, if your variety is defined over a countable field, and you look only at models which are defined over this field. Let's say your variety is defined over Q bar, and you want only to consider Q bar models. But so let me explain. Let me take any a sequence, let's say alpha n, inside this space. And let me explain what this means for this sequence to converge to some other element. So alpha n is converging to alpha. By definition, this means that for any model pi, so this alpha n is in fact is a collection of alpha n pi, right? So if you look at alpha n pi, so this is now an element, a k-numerical class in x pi. And this convergence means exactly that for any model, this converge to alpha pi. And here again, so here I dropped the index, the reference to R. So here again, this is a finite dimensional space, real vector space. So the convergence here is for the standard Euclidean topology. Okay? And yeah, so I talk only about Vi classes and not about Cartier classes because Cartier classes, this is an inductive limit, so it's a union of a finite dimensional, uncountable union of finite dimensional vector spaces. And here, this in functional analysis, everybody knows that it's very complicated. Okay, so you have many different topologies, and so I decided not to talk about any because then they're not a preferred one. Okay, so let's say so on Wahl numerical K classes, you have a nice topology which is locally compact, and on Cartier classes, you don't have anything. Okay. I think I'll stop here so that tomorrow I can start with the volume function. So thank you.